All right, welcome back. At this point, we are pretty much done with everything we wanted to say in the context of frame invariance for hyperelasticity, okay, for solids. We and just recall that in the process we visited this notion of the material tangent. We saw how the material tangent can be obtained once we have a hyperelastic strain energy function. We also saw that the form that strain energy function has to be restricted to. And then we saw that in order to describe things in the current configuration, it's a little more complex, right? And we saw that in the process of describing the material response in the current configuration, we get this new object, the spatial elasticity tangent, which has fundamental geometric nonlinearities in it. So we'll go on now and look at what objectivity and frame invariance imposes upon constitutive relations for fluids. We already saw this in the context of ideal fluids, right? We saw that fluids which have only a pressure part to their stress tensor are already endowed with an objective constitutive relation. Let's go on now to non-ideal fluids, which are basically viscous fluids, and see what happens there. Okay, so we're talking here of the requirement of objectivity on constitutive relations for viscous fluids. All right, okay, so recall. The viscous stress in a fluid. I believe we wrote this out as sigma V, right? The Cauchy stress, the viscous part of the Cauchy stress. And we said that it is a tensor function. Okay? In the most general case, it's a tensor function of the spatial velocity gradient. Okay, and you recall we gave this this example of the parallel plate experiment. Right? We said that, well, you set up a velocity gradient, right? That's how V varies with maybe the x2 direction. Okay, if we have E1 and E2, right? E3 could be coming out of the board here, right? So that's a fixed boundary of a flow. Think of this as a channel flow, right? And we said that if you are now moving along a plate in this direction, right, and you apply a shear stress on that plate, which is say sigma V, right? That's just the magnitude of the shear stress. We said that it is equal to maybe the force, right? And now I have a dilemma in terms of what I'm going to write as a symbol for the force. Let me just write force, right? The force divided by the area of the plate, right? And now if we say that this height is h, and the maximum value of the velocity is Vmax, there, right? The velocity along the E1 direction, right? Reaches the maximum magnitude of Vmax. Then we said that, well, what you will find is that sigma V equals mu Vmax divided by h, right? And Vmax divided by h is essentially the magnitude of the spatial velocity gradient. All right? So this is the basic idea of a fluid that has a viscous response. Okay? Of course, that can be generalized. This is a very special sort of experiment, right? Effectively one-dimensional experiment. And so we generalize that to say that, well, in general, the viscous stress is going to be some tensor function f of a tensor argument, the spatial velocity gradient. All right, so what does objectivity say for us here? Okay, so remember what happens with rigid motions on the current configuration. Okay, so we know that phi plus equals C T plus QTX. Okay, and what we showed some time ago was that what happens now with del plus of V plus, our spatial velocity gradient, is that you get a component which has the form Q spatial velocity gradient Q transpose, and things are looking very good because that has the form of an objective transformation, but there is some amount of residual badness, if you will. Okay? It is not an objective tensor. Okay? It is not objective. All right? And so now we say that, well, what can we now say about constitutive relations for our viscous fluid? We know that the Cauchy stress is objective. Okay? So what one should have is that the requirement of objectivity on our constitutive relation right, is that sigma V plus should be Q sigma V Q transpose. The Cauchy stress is indeed objective, so this viscous component of it, which is just an additive part and a part that we'd add on to the pressure, also better be objective. Okay? But then sigma V plus can be obtained as just F acting on the transformed velocity gradient tensor, right? And Q sigma V Q transpose is just Q F of grad V Q transpose. Okay? So the requirement is that F as a function of grad V should be such that F of the transformed spatial velocity gradient tensor should be Q F of the untransformed spatial velocity gradient Q transpose. All right? Okay, but then that implies, because we know what the transformed spatial velocity gradient tensor looks like, it says that okay, this has to hold. Now remember, this has to hold for all rigid motions, right? So this has to hold for all for all motions, first of all. Okay, and it has to hold for all points x in the current configuration and for all time in the interval of interest. Now, I should just mention that in the context of this experiment that we are carrying out, this is my fluid, right? So now imagine we were carrying out the experiment with this fluid, with the fluid flowing through this bottle. What we're saying is that our stress tensor, our viscous stress tensor, should transform as shown here if we apply rigid motions upon this entire lab, right? We turn the lab around, right? Gravity doesn't act, of course. We turn the lab around and we should conclude properly that the stress components transform as written out here, right? The viscous stress components, right? Alternately, if we change our frame of reference, we say that, well, instead of looking at this lab relative to this frame, I want to look at it relative to that frame. Our components of the stress should transform accordingly, as we've written out here. Okay, and that imposes this restriction upon our constitutive function f. All right, to proceed, observe that this is skew symmetric. We've shown this before. Okay? Okay? Let us call it capital omega. Okay? At the minor risk that you will confuse it with a configuration, right? But it's a tensor, it's not one of our configurations. Okay? All right, we have this. So what we can now write is that our f is q. Now, I'm going to rewrite our spatial velocity gradient grad v in terms of its symmetric and skew symmetric components. Plus yet another skew symmetric component where the capital omega comes from the rigid motion only, right? It is basically the spin rate associated with our lab spinning around, tumbling through space, right? So if you were conducting this experiment out in space, right? That's what it's referring to. Okay. This is equal to q f function of d plus little omega q transpose. Also remember that d is our rate of deformation tensor, which actually played a starring role in the previous segment in the context of hyperelasticity, but now it shows up in the context of fluid flow, right, of viscous fluid flow, and omega is the vorticity of the flow. Right? Little omega is the vorticity of the flow, capital omega is the effect of the lab tumbling through space. All right, both skew symmetric. Okay, skew symmetric. All right. Okay. Now we play effectively the same sort of game as we played in the context of solids, right? We say, all right, you pick a point in the spatial configuration and a time at which you want me to apply my arguments, okay? And I say that now, since this requirement must hold for all q, right, or for all evolutions also of q belonging to SO3, well, SO3 plus really. Since it must hold for all of them, it also holds for a very special one, okay? It also holds also holds for Qt such that at the present time, okay, at the time of interest, Qt is the isotropic tensor. Okay, and the isotropic tensor also is a member of SO3. Okay, so I can say that at the instant of interest, let me consider of all the Qs, it also holds for this particular Q which satisfies this, and furthermore Q dot Q transpose, which is the spinning of our lab, equals minus the vorticity tensor at the point of interest. Okay, it also holds for this. It holds for a whole bunch of them. It holds for all Q, all possible evolutions of Q. All right, it also holds for this one. What this implies then is that our function, okay, if you go back and look at perhaps in your notes, I can scroll back here, look at this function on the bottom, or the equation at the bottom of the slide. Substitute that Q equals the isotropic tensor, capital omega is minus little omega, right? And what we see is that we conclude that f of d plus omega minus let me write this as minus capital omega, but now for capital omega I've said that this is plus capital omega, right? And I've said that capital omega is minus little omega equals QF Q transpose, but we've chosen to look at a particular Q which at the time of interest is equal to the isotropic tensor. Right, so we get f of d plus omega. All right, it holds for a whole bunch of Qs, but it also holds for this one. Okay, now this has to hold, of course, for any. Now I can make this sort of argument for any point x belonging to omega t and for all times. Right? The only way this can work, and well, what happens now? When I apply this, we see that these cancel out, right? Which implies that we see that at every point, what we will conclude is that your function evaluated on d is your function evaluated on d plus on the full velocity gradient tensor. Right? Effectively, we are saying what the only way this can work for every single point and any time is if our function is a function only of d. Right? Okay, so f is a function of the spatial velocity gradient tensor through d alone. Okay? And then f must also satisfy q f of d q transpose equals f of q d q transpose. Okay? All right, for all q. Okay? So at this point, what we've done is essentially an argument which belongs in the same sort of family of arguments as the one that we imposed for hyperelastic strain energy functions. Okay? This was done in the context of rates, however. All right, and we see that essentially it requires that our viscous stress depend only upon the symmetric part of the velocity gradient tensor. Okay, and this again is a fundamental requirement for constitutive relations for viscous fluids. All right, that final requirement of QF, Q transpose has to be F of QD, Q transpose. Okay, can be satisfied, okay, that final requirement is satisfied by f as a function of d, right? If we now expand it as a polynomial, right, we can write it as alpha naught, okay, which is a function of d, but alpha naught is a scalar function of d, times the isotropic tensor plus alpha 1 scalar function of d times d plus alpha 2 also a scalar function of d square. Okay, this is up to quadratic terms. Okay, we can go on, right, essentially expand this as a polynomial. The requirements then are that alpha naught of d, alpha 1 of d, alpha 2 of d, right, should be functions of only the invariants of d, the first invariant, the first principal invariant, the second principal invariant, and the third principal invariant of d. Likewise for alpha 1 and alpha 2. Okay, and you recall that the first invariant of d is the trace of d. The second invariant is 1/2 trace d the whole square minus trace of d square. And the third invariant is determinant of d. Okay? When we have this form, it's not difficult to see that if you now replace f d, but then you multiply it by q and q transpose, pre and post multiplied by q and q transpose, it is essentially q f of d q transpose. Okay, right? Since alpha naught, alpha 1 and alpha 2 depend only upon the principal invariance of d, those scalar functions remain unchanged, right, when we transform d as q d q transpose. Okay, and then the effect of q, right, acts only upon the isotropic tensor d or d square. Okay, so this is a general quadratic model for a viscous fluid. Okay, this is a general quadratic model for viscous fluids. Okay, since it's a quadratic model for viscous fluids, it's also nonlinearly viscous. Right, so special cases are if alpha naught and alpha 2 are both equal to 0, right, then we have f of d. Okay, if alpha naught and alpha 2 are both equal to 0 and alpha 1 is a constant which is equal to 2 times the shear viscosity of the fluid, okay, where mu is the shear viscosity. Okay, all right. Then we have f of d equals 2 mu d. Okay, this is our Newtonian viscous fluid. It's the most common model for a viscous fluid. Okay, commonly used for air and water. Okay, that will be example 1. So the second example of a viscous fluid is one in which we have the following sorts of functions. We have alpha 2 equals 0. We have alpha naught equals kappa trace d, and we have alpha 1 equals 2 mu. Right? In this case, we have that the total viscous stress is as a function of d kappa trace d isotropic tensor plus 2 mu d. This term is what we call a bulk viscous stress. And this would, of course, be the usual shear viscosity. All right. So essentially what we're saying here is that the fluid develops a stress not just because of the effect of shearing action of the flow, but also from the fact that the flow can change volume. Okay, so we have trace D there, so obviously we're saying trace D in general is not 0. It's not an incompressible fluid. Okay, but in the process of compressing the fluid at some rate, which is what we pick up as trace D, we also develop a viscous stress response because of the rate at which the fluid is being compressed. Okay? Okay. And then the third example that we have is one in which alpha 2 is not equal to 0, right? And this in general is a non-Newtonian fluid. It's a non-Newtonian viscous fluid, right, where the viscous stress is non-linearly dependent upon D. I should also add that that case 2 here is sometimes called the Reiner-Rivlin fluid. All right, we'll stop here.